everyone, Chang here and welcome to my channel. Today we're going to focus on this poorly drawn ladder. Well, actually no, we're going to focus on proof by induction. Now here's the thing though, proof by induction is actually slightly different from a lot of the other proof approaches. All the other proof approaches, you might not necessarily know the end result, what you want to prove. You have the luxury of manipulating, working around, and end up finding the result. Proof by induction is not the case. You have to know the end result. And what you're going to do, either through guessing, through pattern recognition, or just somehow having that end result, the proof by induction is used to show that that is valid, that is true. Now, here's the thing. It has two requirements. The first one is that you need a starting point, somewhere to begin. And that's why it's often shown as either a staircase or a ladder. So let's just say here's our starting point. Starting point. Okay, and then afterwards you're going to prove generally that the next step, right, the next iteration, whatever pattern, is valid when the previous one is valid, right? So generally you're going to say, for example, the next step, next is true when the previous is true. Is true. Okay, so that's the idea. You have a starting point, so you could basically step on the ladder, step on the staircase, and if you can show that every single, I guess you could say, iteration, next step is true if the previous one is true and is generalized, then you know that the whole formula, the whole result is going to be true as it goes on to infinity. Because guess what? It's the fact that, all right, well, if this is the starting point, I show that this one is true. All right, cool. So since it's generalized, I mean this one is true because I know this is true, because I know this is true, and so on and so forth. So it builds like a staircase, like a ladder up. So hopefully it will make more sense once we go over certain problems so you can see the proof by induction in action. But remember, these are the two keys. Always have a starting point and always show generally that because the previous one is true, or assuming the previous one is true, the next one is true as well. And just like that, you will end up proving your results. So let's look at a problem. All right, so for our first problem, we have this basic formula right here, right? We have 1 plus 2 plus 3 plus blah, 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 on and on until x, whatever x you determine. And it doesn't matter what x is, the end result is that if you want to find the sum of them all together, you can actually plug it into this formula where you figure out what x is. If x is 10, then you plug in 10. If it's x is 100, you plug in 100. And this result here is going to be the sum of 1 all the way to that particular number. So this is a formula. We want to show that this is valid, right? It looks nice, we can test it a little bit, and it seems to be valid, but we're not sure. So we're going to use proof by induction to show that this entire formula is valid no matter how big or how small that number is. So what can we do? Well, first and foremost, once again, we need a starting point. Well, if it has 1, we can do 1 as a starting point. So we're going to do f of 1, right? And we know that f of 1 is just 1, 1 had nothing. Blah, blah, right? So what we're going to do is we're going to check if this is true. Well, x, we're going to put in 1. So it's going to be 1, and this is going to be 1 plus 1, right, for this x as well, divided by 2. Well, luckily for us, that's 1 times 2 over 2, which is 2 over 2, and then you simplify it to 1. So that's good. We know that at least for the first one, 1 is valid. All right, so we have our starting point. Now, what we're going to assume generally, let's just going to assume, I'm just going to make it here so you can see it, assume in bright red, right, that this statement is true. And this is the weird part. We're going to assume x plus 1 over 2 is true for a generalized f of x. Okay? Now, if we assume this is true and we can show that this kind of format holds for f of x plus 1, the next step, the generalized next step, then this entire formula is valid. So let's do this. F of x plus 1 is basically 1 plus 2 plus 3 plus blah, 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 plus x plus, and then let's just make this red here so you can see it, x plus 1. That's the extra one that we're doing, right? Well, we know, based on the assumption that 1 plus 2 plus 3, blah, 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 plus x is just this guy, right? So we're going to have x x plus 1 over 2. Okay? Plus, now we have our x plus 1, this extra one right here. And of course, using our lovely math skills, basically we're going to do 2 over here and the bottom 2 over here to have them have a common denominator. And then afterwards, we basically have x times x plus 1 plus 2 times x plus 1 over 2. And then you factor out the x plus 1, you have basically x plus 1 times x plus 2 over 2. Okay, cool. How does that help? Well, here's the thing. If we have this is what we figured out. What happens if we plug in x plus 1 instead of just x and see if we get the same result? Well, if we plug in x plus 1 here, that means for all x, we're going to put x plus 1. Well, here, that means we have x plus 1. Here, we're going to have x plus 1 plus 1 over 2. Well, we know we can combine like terms there, so that's just x plus 1, x plus 2 over 2. Well, look at that, right? So even with this, assuming, right, if the previous one is true, the next one is true. We showed that the next one is true. This one and this one is exactly the same. That means this formula itself works generally, right? It doesn't matter what the number is, how big it's small, it works all the way into infinity. So hopefully that makes it a little more clear. Let's look at another problem with the same concept so you guys can, ingrain it into your head how proof of induction works. All right, let's look at this one. This is a pretty infamous one. You might have seen it once or twice, or maybe not at all, but it's a good thing to see it and at least remember it, because guess what? You're probably going to encounter a problem asking you about this. So f of n equals 1 squared plus 2 squared plus blah, 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 plus n squared. Now, in order to find the sum for whatever number it is, the formula itself is going to be n times n plus 1 times 2n plus 1, all divided by 6. Now, this is wonderful, this is great, but we need to show that this is true generally, right? For any number, big or small. So, proof by induction. We need two things. First and foremost, we need a starting point. Well, if it's starting at 1, we're going to test that. And then after that, we got to show that based on the previous, if we assume the previous one works and then we show the next one works, then it works generally. So, let's do this. First and foremost, our starting point, f of 1 is just first one, 1 squared, which is just 1, okay? But we need to show that this formula is true. So what we're going to do is for all of n, we're going to plug in 1. So we have basically 1 times 1 plus 1 times 2 times 1 plus 1, all divided by 6. Well, 1 plus 1 is 2. 2 times 1 is 2 plus 1 is 3. So basically we have 1 times 2 times 3 equals 6. Well, if that's the case, that's just 6 over 6, which is 1. Great. There is our starting point. Now, after that, we're going to show the generalized one. And the math is probably going to be tedious, so hopefully I don't make a mistake. All right. Well, let's see. Assume f of n, the statement, is true. We want to show that the next one, f of n plus 1, is going to follow under this general structure. So let's look at that. F of n plus 1 is just 1 squared plus 2 squared plus blah, 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 plus n squared plus n plus 1 squared, right? And we know, based on our assumption, that this is true for just f of n, right? So we know that 1 squared plus all the way to n squared is just this right here. We can actually substitute that. So we're going to have n times n plus 1 times 2n plus 1 over 6 for this guy right here, plus, and this is going to be n plus 1 squared. And of course we don't like that because they're not common denominators, so we're just going to multiply top and bottom by 6 as well to make it easier. So basically, in the end, we're going to have n times n plus 1 times 2n plus 1 plus 6 times n plus 1 squared, all over 6. Okay, so that's what we have so far. That's a lot already. Whew. All right, well, these have n plus 1, so we're going to factor out n plus 1. That's just going to give us n plus 1 times, and whatever's left over. We have n times, what is that? 2n plus 1 plus 6 times n plus 1 all over 6. Okay, please check my math. All right, cool. So what do we have next? All right, well, in that case, here is the one that we're a little worried about. So we're gonna just distribute everything, and what do we have? We have basically, well, we still have our n plus 1 on the outside. Inside now we have, what is that? 2n squared, and that's gonna be plus 2n, and that's gonna be plus, what is that, 6n? Yes, 6n, and then plus 6. Boom. Okay, so what do we have? All right, well, if that's the case, we can combine like terms here. We have, and don't forget the over 6. n plus 1 times 2n squared. I feel like I'm making some sort of mistake. Why do I feel that way? Because it is not 2n. It is just n. All right. Trust your intuition. All right. Plus 7n plus 6 over here, all divided by 6. Okay, cool. All right. Well, if that's the case, here's where I cheat a little bit. I want it to be basically this structure right here. Now, I can try to factor this out, and we can definitely do that. But if that's the case, and I'm looking for f of n plus 1, if this is valid, basically this would end up being f or n plus 2, and this one's going to be what? 2 times n plus 1 plus 1, so that's going to be 2n plus 3. If I can show that this guy is the same as n plus 2 times 2n plus 3, right? Then I'm good. So let's just do that. N plus 2 times 2n plus 3, what do I get? I get 2n squared, right? N times 2n plus 3n plus 4n plus 6. This combined to become 7n. So yes, we're good. So basically, if we were to factor this out, we have n plus 1 times n plus 2 times 2n plus 3 over 6. Okay, so whew, that's a lot of stuff, right? It's like blinding at this point. But basically, at this point, we're done. Now, how are we done? Well, if this is the case, if this is the formula, and I plug in n plus 1 for every single one of them, right? I just sort of indirectly shown. But if I plug in n plus 1 for all of them, the end result is going to be basically this guy right here. And since I've shown that assuming that f of n is true, f of n plus 1 is this, and if we plug it in the generalized formula, it's the same thing, then it's true, right? The next step is true based on the fact that the previous one is assumed to be true. And since we have a starting point and we have that second part, then overall this generalized formula works. So let's look at another one that's actually slightly different. Alright, so I've given you one blinding problem. I'm not going to give you guys another blinding problem. Now here's the thing though. This problem is slightly different from all the previous one we looked at. All the previous one we had a starting point, right? But that's not the case. Certain problems, even though proof by induction works beautifully on them, requires multiple starting points. This is one of those problems. And this one's only 2. There's going to be problems that require 3. It's going to require 4, so on and so forth. Read the problem and make sure that you got all the required starting points. And after that, you show that whole generalized next step thing, and it will work. So the reason we know that this one required 2 is first and foremost, it gives us 2. The other one is notice that this one requires the previous iteration, and this one requires not the previous one, but the previous one, right? So that's why you have to show both starting point works, and then this generalized form, and therefore complete the entire proof. So let's look at this really quickly. A sub n equals 1. A sub 2 equals 3. Or sorry, a sub 1 equals 1. I misspoke on that one, right? And a sub n equals 2 times a sub n minus 1. That's the previous iteration, and that's why I put an underline so that my horrible handwriting don't get confusing too much, right? And then minus a sub n minus 2. That's the previous iteration. Then this formula right here, a sub n equals 2n minus 1. So what we have to do is check that these two are true, right, as good starting points, and then the generalized step So let's do this. A sub n, or a sub 1 equals, well, in this case, since we're looking at n equals 1, that's going to be 2 times 1 minus 1. 2 minus 1, 1. Good. First starting point, valid. Second one, a sub 2, right? That's where our n is, equals 2 times, now it's going to be 2, right? Based on this formula. Subtract 1, that's 4 minus 1, 3. Good. Both starting point works. Now, we have this guy and we have this. Now, here's the thing. We want to show that a sub n plus 1 is going to fall basically in this generalized, I guess you'd say, format, right? It's going to be 2, and in this case, it's going to be n plus 1 minus 1. All right, so, well, a sub n plus 1 is going to be, based on this right here, should be 2 times a sub n minus a sub n minus 1. And let's just make sure it's not confusing. There it is. Okay, cool. Now, we're assuming, right, this statement is true. A sub n equals 2n minus 1. And so, a sub n minus 1 should be 2 times n minus 1 minus 1. And if we simplify that, that is 2n, and that is minus 3. Okay, so we have our assumption of this guy being true, and based on that, assumption of this guy being true as well, because that's the previous iteration. So, there it is. Well, if that's the case, let's plug it in. 2 times a sub n, that's going to be 2n minus 1, right? That's this guy right here, minus, and then this whole thing right here, 2n minus 3. That gives me 4n minus 2, and this is going to be minus 2n plus 3. So we combine like terms, what do we get? We get 2n, and then negative 2 plus 3, that's going to be plus 1. All right, cool. So we have this guy. Now we have to show that if we plug in a n plus 1, a sub n plus 1, that's going to be 2 times n plus 1 minus 1, which is 2n plus 2 minus 1, or 2n plus 1. Good. So there it is, right? Notice 2 starting points. We showed that based on the assumption of if the previous step works, the next step works. So if this is assumed to be the previous step, we showed that the next step, the n plus 1, works as well. So that means it generalizes this whole formula. So it works, right? That's how proof of induction basically works. All right, so we're at the end of the video now. Hopefully this is not too confusing, right? This is a very basic or very elementary introduction of proof by induction. Now, once again, there are 2 main parts to this proof. You have to have a starting point, a starting point or multiple starting point based on the problem itself. You just have to make sure you cover all of your bases, right? You check it, make sure that whatever results, whatever formula you're trying to prove works for those starting points. After that, you prove that generalized step. The generalized step is that based on the assumption that the previous iteration, the previous step is valid, it's true, the next one is true as well. And since it's generalized overall and you have a starting point, then you can basically build your staircase or your ladder. And so it expands all the way to an infinite amount of number, and that formula just works. That's the whole point of proof by induction. So, once again, thank you for watching this video. If it's made you more confused, then my bad, right? If not, then thank you. Please like, comment, and subscribe. I will see you in the next video.